الله الرحمن الرحيم. Chemistry 108, General and Organic Chemistry, Chapter 2. Chapter 2, Atoms and the Periodic Table. This chapter we will discuss the following items: atomic theory, elements, and isotopes, and so on. The atoms are the building blocks of compounds. Compounds made by atoms. Chemistry is founded on 4 assumptions, which together make up atomic theory. First, atoms, all matter is composed of atoms. Atoms of a given element differ from the atoms of other elements. For example, atoms of oxygen are similar together but different from nitrogen atoms or hydrogen atoms. Chemical compounds consist of atoms combined in a specific ratio, where this ratio should be in whole number, integer number. For example, to form water from hydrogen and oxygen, the formula should be H2O, means 2 atoms of hydrogen with 1 atom of oxygen. The ratio should be in whole number, not in fraction. Chemical reactions change only the way atoms are combined in compounds. Water molecules result from hydrogen and oxygen by changing the ratio and changing the bonding between hydrogen and oxygen. Hydrogen H2 with oxygen O2 will change to form water. 2 hydrogens combined with 1 oxygen. So chemical reactions change only the way atoms are combined in compounds. Now let's take a look on atomic view. The atoms are composed of tiny subatomic particles called protons, which is positively charged, neutrons, which is uncharged, while electrons, which are negatively charged. Protons, neutrons, and electrons. Protons, positively charged particles. Neutrons, uncharged, while electrons have a tiny mass relative to mass of neutron and proton. And mass of electrons is so negligible relative to mass of neutrons and the protons, while electrons are negatively charged particles. This summarizes these properties for protons, neutrons, and electrons. Simple proton P, neutron, and electron E. The masses scale AMU, proton and neutron almost the same mass, about 1 AMU. The AMU is the unit used to express the mass of these subatomic particles, while electron is 5 multiplied by 10 to the power minus 4, which is very, very small relative to mass in neutron and mass the proton, so is negligible. The charges the proton partially positive, neutron uncharged, and the electron negatively charged. The masses of atoms and subatomic particles are expressed on a relative mass scale called atomic mass unit, based on the mass of carbon. You can measure the mass of any element compared with the carbon-12. The view of the atom, like the solar system, نظام الشمسي, the center nucleus, one nucleus contain protons and neutrons packed together, closely together, in a dense core, almost a distance about approximately 10 to the power minus 15 meter, while electrons move around the nucleus in the vacuum around, or the volume around nucleus in slightly large volume. So the mass of atom mainly is the mass of nucleus, while the volume of atom is the volume occupied by electrons. The volume occupied by electrons approximately about 10 to the power minus 10 meter relative to the distance of the nucleus, which is 10 to the power minus 50. So nucleus is very dense because the mass is high and the volume is low, small, volume with high mass is a dense core called the nucleus. Surrounding the nucleus, the electrons move about rapidly through a large volume of space. So mainly the volume of atom is the volume of this space of electrons, while mainly the mass of atom is the mass of the nucleus. The opposite electrical charges attract each other, plus protons with minus electrons attract each other, opposite charge attracts, while similar charges or like charges are repel each other. Electron repulsion. There is a repulsion between electron and proton. Like charges repel each other. The atom of a given element is specified by two quantities: atomic number Z, which is the number of protons in atoms of a given element, which is always the same for the same element and different if you change the element. All atoms of a particular element have the same number of protons in the nucleus. Carbon, for example, contains 6 protons. Any carbon atom should contain 6 protons. Mass number is the sum of protons and neutrons. This quantity is called mass number A. Now, any atom of any element is uh, uh, specified by a letter, simple, and two quantities: atomic number Z and mass number A. Usually, the atoms are neutral, uncharged, means have no net charge. In this case, the number of protons should be equal number of electrons, the number of positively charged protons equal the number of negatively charged electrons. In the natural atom, always a natural atom or neutral atom is uncharged. For example, carbon contains 6 protons. Carbon should contain 6 electrons to be uncharged, to be neutral. Example, phosphorus has atomic number C equal 15. This means there are 15 protons. How many protons? 15 protons. How many electrons for phosphorus? Phosphorus atom is uncharged, so the number of electrons should equal the number of protons. So there are 15 electrons in phosphorus atom. Mass number of phosphorus A equal 31. To calculate the number of neutrons, you should subtract 31 mass number by 15 atomic number. Difference between these quantities, you can calculate the number of neutrons. 31 minus 15 equals 16 neutrons. So you can identify this atom by counting number of protons, electrons, and neutrons. Another example, atom contains 28 protons and has mass number 60. Give the number of electrons. The number of electrons should equal number of protons, which is 28. Number of neutrons is the result by subtraction 60 minus 28. You can calculate number of neutrons, identifying the element by counting the 28th element in the periodic table to know this atom, which is this atom. Isotopes, sometimes a given element found in more than one isotope. Isotope are atoms with identical atomic number, the same atomic number, but different in mass number, which is result from the difference in the number of the neutrons. Number of neutrons different, while the number of protons identical. For example, hydrogen found in nature in 3 isotopes. Protium, which is the most abundant isotope نظير الأكثر شيوعا في الطبيعة. Protium contain 1 proton without neutron called H11. H1 atomic number, 1 mass number, means there is 1 proton and no neutron in this isotope. More than 99% of hydrogen in the nature is protium. The second isotope, deuterium. Deuterium is hydrogen because it contains just 1 proton, but with 1 neutron. 1 proton, 1 neutron. This isotope hydrogen, H12, 1 atomic number, 2 mass number. The third isotope of hydrogen is tritium. Tritium H13, 1 atomic number, means there is just 1 proton, but with 2 neutrons. In the nucleus, the protium, no neutrons, just 1 proton. Deuterium, 1 proton and 1 neutron. Tritium, 1 proton and 2 neutrons. Can be these isotopes can be distinguished one from another by writing the symbol for hydrogen H capital. 1 atomic number means 1 proton. 3 for tritium means 1 proton and 2 neutrons. The total sum 3. Deuterium should be H12, 1 proton, 1 neutron, while protium isotope is H11, 1 proton, 1 mass number, 1 atomic number. The isotopes of most elements do not have distinctive names. So, for example, for the uranium, you should write the name. After the name, you should mention the mass number. Uranium 235. First isotope or radioactive isotope نظير المشع لليورانيوم 235. non radioactive uranium isotope is uranium 238. 238. To distinguish between 2 isotopes, you should write the name, and after the name you should mention the number of mass number. Most naturally occurring elements are mixture of isotopes. The uranium in nature is a mixture of uranium 235 and 238. Uranium 235 radioactive, while uranium 238 is not. And uranium 235 radioactive is used in nuclear reactors في المفاعلات النووية في صناعة الأسلحة النووية في nuclear weapons. Atomic weight measured by measuring the average mass of all isotopes of an element. The atomic weight is calculated as the sum of masses of the individual isotopes for that element using their abundance, their percent in nature. For example, gallium has two isotopes. Gallium 69 with abundance percent 60.4 and gallium 71 with abundance percent 39.6. To calculate the atomic weight, use this low atomic weight, sum of isotopic abundance multiplied by isotopic mass to calculate the average atomic weight of two isotopes. Abundance percent isotopic abundance multiplied by isotopic mass for first isotope plus isotopic abundance multiplied by isotopic mass of the second. Another example, identify element X given the atomic number and mass number. X atomic number 78, mass number 194. From these quantities, you can calculate the number of protons, which is equal 78, number of electrons 78, and the number of neutrons 194 minus 778. Periodic table format listing all known elements where the atomic symbol, name of the element, and atomic mass are given in each box that represents the element. Each element specified by a letter symbol, by atomic mass and atomic number. Dmitry Mendeleev, Russian scientists, arrange these elements according to their atomic number in periodic table. This is the periodic table made by Mendeleev, arranged elements according to their atomic number. First atom, hydrogen, which contain proton, helium, 2 protons, lithium, 3 protons, beryllium, 4, and so on. This arrangement according to the atomic number of elements. In the periodic table, the element classified into 3 main categories. All elements on the left side of the periodic table are metals in the yellow color, and elements on the right side of the periodic table are non-metals, while in step stairs in purple color, metalloids. Metals, non-metals, and metalloids. Metals classified by their physical properties. الميتال are malleable element with lustrous appearance. في لمعة lustrous, that's good. That is a good conductor of heat and electricity, found on the left side of the periodic table. Non-metal elements, that is a poor conductor of heat and electricity, occur on the upper right side of the periodic table. Second class. Third class, metalloids, which is intermediate. Their properties intermediate between metal and non-metals. The metalloid are located in a zigzag band between the metals on the left and non-metals on the right. They are 7 or 6 elements: boron, silicon, germanium, arsenic, and so on. These elements, these 6 elements, are called metalloids because their properties are intermediate between metals and non-metals. They are semiconductor of heat and electricity, while metals good conductors, while non-metals are bad conductors of heat and electricity. So these elements can be classified to 3 main categories: metals, non-metals, and metalloids. Elements can also be classified by chemical behavior. Elements in the same vertical column, called groups, have similar chemical properties and can be categorized in the following three groups. The main group elements, which is group 1A to 8A, these elements called main groups or representative groups. In the middle, there are transition metal elements, العناصر الانتقالية in the periodic table. Uh, these are transition metals, and the third class to uh, below the periodic table called inner transition metals, elements, actinides, lanthanides or actinides. Lanthanides, this lanthanide, this element called lanthanide, two rows, lanthanide and actinides called inner transition metal elements, elements. Some characteristic of different groups. Group 1A, first group of many groups. Group 1A called alkali metals, start from lithium and francium. They are shiny, soft metals with low melting point, react with water to form products that are highly alkaline or basic solutions. Lithium, sodium, react with the water to form an AOH and LiOH. They are basic or alkaline solution. And they are highly reactive, sometimes explosive when react with the water or with the oxygen, with air oxygen. Uh, for this, they are never found in nature in a pure substance, because it is highly reactive. Group 2A called alkaline earth metals. Alkaline earth metals also lustrous silvery metals, have a luster, less reactive than their neighbors, group 1A, but still reactive, relatively less reactive than 1A. These reactivity let them never found in nature in a pure state. بيتفاعلوا never found in nature in a pure state. Group 7A also famous group called halogens, fluorine, chlorine, bromine, iodine, and statine. These are called halogens, colorful and corrosive nonmetals. They are nonmetals found in nature only in combination with other elements such as sodium with chloride, table salt, ملح الطعام. The group name halogen is taken from the Greek word halos, means salt. هذه تكون أملاح، هذه groups form salts with metals. Halogens are non-metals with metals form salts like NaCl, NaBr, and Ai. These elements called halogens. Group 8A, noble gases, or sometimes called the inert gases, helium, neon, argon, krypton, xenon, and radon. They are noble because their outermost shell filled with electrons, so they are inert. Noble gases or inert gases, they are colorless gases. Noble because labeled the noble gases because of their lack of chemical reactivity. They are rarely reactive because their outermost shell is filled with electrons. There is no motive force for reaction because their outermost shell is filled with electrons. Helium, neon, and argon do not combine with other elements lighter atoms, while krypton and xenon, heavier, are combined with very few. These some examples of groups with common names for group 1A alkali metals, common name for group 2A alkaline earth metals, halogen for 6A, 7A, or 8A noble gases. Properties of the element are determined by the arrangement of electrons in their atoms, called electronic configuration. The arrangement of electrons in their atoms called electronic configuration. So the properties of the elements are determined by this electronic configuration, which is the arrangement of electrons in their atoms. Solving wave functions, Schrodinger equation, provide an electron with an address within an atom composed of shell, subshell, and orbitals, to distinguish electron from electron by these quantities, these features, shell, subshell, and orbitals. Shell, a grouping of electrons in an atom according to energy, سويات الطاقة, energy level, shell 1, shell 2, shell 3, starting from shell 1, shell 2, shell 3. These groups according to energy level, energy 1, level 1, level 2, level 3. Shell number, for example, energy level number 1, um, electron capacity 2 electrons. Shell number 2, second energy level 8 electrons. Third 18 electrons in 4. Shell 4, shell number 4, 32 electrons can occupy 32 electrons in shell 4, 18 electrons in shell 3, 8 electrons in shell 2, and 2 electrons in shell 1. As the shell far from the nucleus, it became larger, and more electrons it can hold, and the energy is higher. Subshells, there are 4 subshells: S subshell, B subshell, D subshell, and F, according to increasing the energy, depend on the energy within each subshell. Each subshell contain orbitals. Electrons are grouped into orbitals. Orbitals are regions of space within an atom where the specific within an atom where the specific electrons are most likely to be found. The shape S subshell, for example, has 1 orbital, while B subshell has 3 orbitals, D 5 orbitals, and F subshell has 7 orbitals. Each orbital maximum can occupy 2 electrons. So shell number 1, energy level 1, subshell just S, 1 number of orbitals 1. So you can occupy just 2 electrons in this orbital. While energy level number 2, or shell number 2, contain 2 subshells, S and P. S with 1 orbital, P with 3 orbitals, 4 orbitals in second shell. Each of them can occupy just 2 electrons. So net electrons in second shell is 8. Shell 3, shell number 3, contain subshells S, P, and D. S with 1 orbital, P with 3 orbitals, while D with 5 orbitals. If you count the number of electrons, 2 in S, 6 in P, 10 in D, in total 18 electrons, and can occupy a third shell. Shell number 4, or fourth shell, contain subshells S, P, D, and F. S with 1 orbital, P with 3, D with 5. F subshells has 7 orbitals. Total electrons 2 in S, 6 in P, 10 in D, and 14 in F. Total 14, 24, and 8, 32 electrons can occupy the fourth shell. Each orbital holds only 2 electrons, which differ in a property known as spin. Spin upward or downward. If an s orbital occupied by 2 electrons, one of them should be upward spinning and second downward spinning in electronic configuration. Shape of these orbitals as a sphere, while the orbitals are dumbbell shaped ذوات رفع الأثقال dumbbell shaped شكل P two loops in the x-axis, 2 loops in the y-axis, or 2 loops in the z-axis. The summary of electronic distribution in atoms: shell number, subshell S, number of orbitals 1, number of electrons that can be occupied in this shell 2, total electron capacity in shell number 1, 2. Second shell contain S and P subshells and the total 8 electrons. Third shell total electrons 18, while fourth shell total electrons that can occupy this shell is 32. Occupy S, P, D, and F subshells. How many electrons? Example: how many electrons are present in an atom that has its first and second shells filled? First shell filled with 2 electrons, second shell filled with 8, some 10 electrons, and has 4 electrons in the third shell, so total number of electrons is 14. 2 in first shell, 8 in the second, and 4 in the third. So total is 14 electrons, means 14 protons. We know the atom always the number of protons equal number of electrons, so count the number of electrons 14, and the atomic number should be 14. The 14th element in the periodic table is silicon. From the periodic table we can name the element. The element is silicon. The exact arrangement of electrons in an atom's shell and subshell is the atom's electron configuration or electronic configuration توزيع الإلكتروني. There are 3 rules for writing electronic configuration. 1, start filling the electrons with the lowest energy orbital available. Electrons occupy the lowest energy shell. This is complicated by crossover or overlap energy above 3p, like this. Above 3b shell 3b, there is overlap between shells. Shell 4 with shell 3, shell 5 with shell 4 overlap. Electrons fill orbitals from the lowest energy orbital upward. Start with shell 1. If the shell 1 is filled, now start filling in shell 2 and so on. But we must take in consideration there is an overlap above the 3p level. The energy level diagram can be used to predict the order in which orbitals are filled. This scheme shows the priority of orbitals to be filled first, 1s, second 2s, third 2p, and 3s, then 3p, 4s, and so on. This scheme for electronic configuration from the lowest to the highest energy level. Rule 2. Each orbital can hold only two electrons, as mentioned before, which must be with opposite spin. If two electrons in one orbital, one of them should be spin upward, second should be spin downward. Third, three, two or more orbitals with the same energy are each half filled by one electron before any one orbital is completely filled by the addition. This like this. If you will now start filling 1s2 و 2s2 for البورون الatomic number 5 fill first shell, then second shell. Now P has three orbitals, P subshell has three orbitals. If the carbon now second electron B in B empty in Bx filled in Bx. For nitrogen for example هذه تطبيق rule 3 إذا كان عندي suborbitals عندي subshell B with the same energy هذه rule 2 rule 3 if two or more orbitals with the same energy like B has three orbitals with the same energy first fill them to have filled before like oxygen now oxygen after nitrogen. Now you can pair two electrons in one orbital, but since B with three orbitals of the same energy you should have filled them before the pairing of electrons. هذا الأكسجين now you should pair two electrons in one orbital, but for nitrogen three electrons should be half filled. Each of these three electrons should be in different orbital Px, Py, Pz to be half filled. So rule 3, when two or more orbitals with the same energy, each of them are filled by one electron before any one orbital is completely filled by the addition of the second electron. The number of electrons in each subshell is indicated by a subscript. That is subscript for S, two electrons for 2s, two electrons, P, three subshells, three orbitals, each of them with two electrons, total 6 electrons. Now second shell, 2s2, 2p6, 8 electrons in the second shell, and the first shell, 2 electrons in the first shell. Now for magnesium, because the atomic number is 12, add 10 to fill first and the second shell, and 2 electrons in the third shell. This table show the electronic configuration of the first 20 elements, starting from lowest energy level and go up. One for hydrogen, 1s1, for helium, 1s2, and the first shell is filled. Now move to the second shell, and the lithium, 3 electrons, 2 in the first shell and 1 in the second shell, 2s1, and so on. هذه for electronic configuration for the first 20 elements. Obey the 3 rules, or apply 3 rules for electronic configuration again. Rule 1, start the electronic configuration from the lowest energy level. Electrons occupy the lowest energy level, then higher and the higher. but take in consideration there is overlap between shells starting from 3B level and up. So use this scheme to fill electrons uh, from the lowest to the highest. Third, second rule, each orbital cannot occupy more than 2 electrons, while these electrons should be with opposite spin. If two or more orbitals with the same energy, each should be half filled by 1 electron before any one orbital is completely filled. A graphic representation can be made by indicating each orbital has a line, for 1s2, 2 electrons, for 2s2, 2 electrons. For boron atomic number equal 5. So 5 protons means there is 5 electrons. 5 electrons to be electronic configured in 1s2, 2 electrons, and 2s2 second shell. 2 electrons to be there, the fifth electron in 2p. Beryllium 6 protons, 6 electrons. البورون after البورون carbon 6 protons 6 electrons. apply rule 2 and rule 3. هذه rule 3 6 electrons in Py Px because the energy is the same. Now these orbitals should be half filled before completely filling. There is shorthand using noble gas to simplify the electronic configuration. This is the electronic configuration 1s2 for helium. So you can use helium and complete after helium 3 electrons in 2s1, 2s2 and 2p1. Shorthand using noble gas configuration is very useful for large atoms to simplify the electronic configuration. Helium start after helium 2 electrons. For carbon, after 2 electrons, there are 4 electrons should be filled in 2s2 and 2p2. Nitrogen, the same thing, helium 2s2, 2p3. Oxygen, oxygen, helium start filling after 2 electrons. These are the electrons configuration for the oxygen to neon oxygen F هذا النوبل gas هذا filled with electrons. The first shell is filled with 2 electrons. The second shell filled with 8 electrons. Noble gas is stable because the outermost shell, second shell, is filled completely. Show how the electronic configuration of magnesium can be assigned. Magnesium 12 atomic number. The first shell should filled with 2 electrons. The second with 8 and 2, 10. So remain 2 electrons should be in the third shell. So the electron configuration of magnesium is like this. 1s2, 2s2, 2p6. Third shell should contain 2 electrons, or with the shorthand model, can use neon 10 electrons complete filling the 2 electrons in 3s2. Write the electronic configuration diagram of phosphorus. Write the electron diagram for phosphorus. See atomic number 15. Now you can use neon as the noble gas before phosphorus. neon 10. So 5 electrons should be filled after neon 3s2 3b. This is the diagram. Uh, this is the configuration of neon to 1s2, 2s2, 2p6. This is the configuration of neon. 5 electrons filled in 3s2 and 3p3. In each orbital, 2 electrons should be with opposite spin. Always 2 electrons in certain orbital should be with opposite spin. Electron configuration with the periodic table. Main group 1A to 8A, orbital used in the filling of electrons S and P, while the transition metals, the middle, introduce d orbitals in the filling of electrons, while inner transition metals use F subshells. So you can classify the main groups transition metals, while inner transition metals by which orbital or which subshells used in the filling of electronic configuration, filling of electrons in the electronic configuration. The main group always use S and P, the only orbitals used in electronic configuration of main groups S and P, while transition metals used the subshells. The inner transition metals use the F subshell in the electronic configuration. Elements in the same group of periodic table have similar electronic configuration in the valence shell. The valence shell, the outermost shell, called valence shell, and their electrons called valence electrons. The properties and behavior of elements depend on the outermost shell electrons, the valence electrons, not in the inner electrons. Inner electrons doesn't make sense in the property or behavior of elements. The key figure in these properties and behavior are valence electrons. Valence shell is the outermost electron shell of an atom, مدار الخارجي الفلك الأخير. Valence electrons, electron in the valence shell of an atom. This is the, for example, group 1A, lithium and sodium, potassium. There is one valence electrons. They have one valence electrons, while group 2A, 2 electrons, and so on. So these groups are similar in their valence electrons, so they are similar in their properties and behavior. بتشابهوا بخواصهم الكيميائية وتفاعلاتهم والreason the similarity in their properties is they have the same valence electrons. Valence electrons properties and behavior depend on the valence electrons. Noble gases, helium, neon, are inert material because their outermost shell is filled with electrons, so there is no need to be reactive to reaction. Always element react to fill their outermost shell with electrons to be stable, to reach the stability of noble gas by filling the outermost shell. Write the electronic configuration for sodium. Sodium 11 protons, atomic number 11 means 11 protons. Sodium in the atomic state, number of electrons should be equal number of protons. So sodium has 11 electrons. To write the electronic configuration for sodium 1s2 2 electrons, 2s2, 4 electrons, 2p6, 10 electrons. So after a neon configuration, 3s1 last or the outermost shell of sodium is shell 3, where shell 3 has 1 electron in 3s. So in configuration neon for sodium, neon and 3s1. هذا توزيع هذا للصوديوم، هذا الصوديوم 3s1 after neon. Atomic number is 11, neon is 10, one sodium after neon by 1 electron. This 1 electron in 3s1 subshell, and so on. Cl and zirconium, you can write the electron configuration in the same way, using N to represent the number of valence shell for group 6A. 6A means the valence electrons of 6A groups is 6. 6, 2 in S and 4 in B. So NS2, NB, 4, general formula for the electronic configuration of group 6A. For group 6A, the general valence shell configuration is NS2, NP, for the sum of electrons 2 plus 4, 6. 6A always contain 6 electrons in the valence shell. How many electrons are in a 10 atom? 10 atom with atomic number 50 protons. Periodic table 10 Sn has atomic number 50, so it found in group 4A valence electrons 4, the number of electrons the outermost shell is 4. This is the configuration in shell 1, 2 electrons, in shell 2, 8 electrons, in shell 3, 18 electrons, in shell 4, 18 electrons, and the outermost contain 4 electrons. So there are 4 valence electrons in 10. How many valence electrons in 10 atom? 4. The general formula for group 4A 5s2 5p2. Electronic dot symbol, because the most important electrons for properties and behavior are outermost shell or valence electron shell. Lewis concern with the valence electrons and represent them by dot. Each electron valence electrons can be represented by dot, an atomic symbol with dots placed around it to indicate the number of valence electrons. Group 1A has just 1 electron. Group 2A, 2 electrons represented by 2 dots. Group 3A, 3 electrons, and so on. After group 4A, 4 electrons with the carbon silicon with 4 dots. Now start for nitrogen. After 4 electrons, put the 5th electron in pair. In nitrogen there is 1 pair of electrons, زوج من الإلكترونات مزدوج, و 3 unpaired electrons. 3 unpaired electrons و1 paired electron. For oxygen, after 4 electrons, the 5th electron should be paired with 6th electron should be paired. So the oxygen have 2 electron pairs و 2 unpaired electrons. 2 unpaired electrons, 2 غير مزدوجين و2 مزدوجين. for الF 7 electrons. after ال 4 unpaired, ال 5th should be paired, the 6th should be paired, the 7th should be paired. So result halogens has 3 lone pairs و 1 unpaired electron. noble gases 8 found in 4 pairs, 4 electron pairs، 4 أزواج من الإلكترونات. هذا لويس to simplify atomic configuration and concentrate on the valence shell electrons, represent them as dots. The electron dot symbols for some main group elements. Write the electronic dot symbol for an element X in group 5A. 5A means there are 5 electrons in the valence shell. 5 valence electrons can be represented by dot, dot, dot. After 4, the 5th electron should be paired. So the result 1 pair and 3 unpaired electrons like this. This the solution. This element X element has 3 unpaired electrons and 1 pair of electrons,